A rod AB has mass m and length 2a. I'll just get the 2a labeled on the diagram. It has its end on rough horizontal ground, that's A, and then against a smooth vertical wall. Makes an angle theta with the ground and is resting in limiting equilibrium. So let's write on some of the forces here. There's going to be a normal reaction at B. There's going to be a weight, but we don't yet know where it's being applied. Actually, it says later on that it's going to be uniform. So, okay, I won't write anymore, but I will just add that at the moment. There's going to be a normal reaction then coming up. That's going to balance out the weight. So the friction, it must be going to the right because that is balancing out the normal reaction. If it was going to the left or not there, then it would slip to the left, and we know it's in limiting equilibrium. It's not actually moving. So friction acts to the left. Sorry, acts to the right to balance normal reaction from the wall. The magnitude, the normal reaction of the wall on the rod is S. So I normally call it RB, but they've asked us to call it S here. And then, like we said, the rod's modeled as being uniform. So I'm now going to add this force on. It's going to be mg, the weight, and it's going to be there's going to be an angle here of theta. And then I'll just say that this is FA and this is RA, and we are ready to go. So by taking moments about A, show that S is a half mg cot theta. Moments about A. Well, there's going to be a clockwise moment from the weight. And remember, because it's uniform, this distance here is going to be A. And so is the distance here to here. So we're going to take the component of the weight that is perpendicular to the rod because it doesn't cause a turning force for the component going to the left. Sorry, not left, down from B to A. So it will be mg, then cos theta multiplied by A. And that must equal the anticlockwise moment coming from S. Now I didn't add that on, but this is also theta because we've got, you can see alternate angles here, or Z. So it would be S cos theta that would then be going this way because it'd be turning it into the angle, it would be adjacent. So it's going to be S sine theta. And then I'm timesing by 2a. I can cancel out the a's. So S is going to equal 1 over 2, just divide by 2, mg cos theta over sine theta, which becomes a half mg cot theta. Coefficient of friction between the rod and the ground is mu, and then we're given that tan theta is 3 over 4. Now that immediately means that cot theta is 4 over 3. And we're asked to find the value of mu. So what we can use is the frictional force, Fa in this case, is equal to mu Ra. It's normally less than or equal to, but we're told here it's in limiting equilibrium, so it's equal. And that means mu is equal to Fa over Ra. We've just got to work both of these out. But the nice thing about this question is that there's only two forces going horizontally, so they must be equal. It must be that Fa is actually equal to S. So resolving horizontally, Fa equals S equals a half mg cot theta, which is going to be a half mg times 4/3, which is 2/3 mg. And then resolving vertically, we're going to get the normal reaction at A is equal to the weight, so Ra is mg. And therefore, mu equals 2/3 mg over mg, which is just 2/3. Then we're asked to also find in terms of m and g the magnitude of the resultant force acting on the rod at A. So that's going to be well, we call it the contact force as well, the normal reaction and the frictional force combined. So we've just said that the frictional force was 2/3 mg, so that's acting to the right. And the normal reaction is mg, it's the same as the weight. So we want to know the length of this vector here. And we can just use Pythagoras. Mg, now, okay, I'm going to show you it in two ways. You could do mg squared plus 2/3 mg squared square rooted. That's probably how you might have done this. So we'll get m squared g squared plus 4/9 m squared g squared square rooted. 1 plus 4/9 is 13/9, so 13/9 m squared g squared square rooted, which gives root 13/3 mg. Just square root them separately. So that's the contact force, or the resultant of the reaction and the friction. There's actually a slightly quicker way we could have done this. Because they're multiples of mg, well, we could have kind of just taken it out. Like, imagine that it was just 1 and 2/3. You would just do 1 squared plus 2/3 squared. And if you then times it by mg, you would just, times it by the end. Don't even need to worry about involving it in the Pythagoras. Alternatively, you could square it and then square root it, but you get back to the original. And then you just get, I'm just trying to say, because it is actually slightly simpler if you realize that. But no worries if not. So that is it, root 13/3 mg. And finally, in a new model, the rod is modeled as being non-uniform, with its center of mass closer to B than to A. So for example, here, a new value for S is calculated with tan theta the same angle. State whether this new value is larger, smaller, or equal to the value that S would take using the initial model. So let's have a look at what we were doing in the calculation. It's still going to be very similar to this here. So the right-hand side would remain the same, but the left-hand side, now this would become larger because we're further away from the pivot. So basically the moment created by the weight will be larger. Let's imagine if it was, it was here, it was like 1.5a. It's going to be 50% as big. We're going to be times them by 1.5. And what that means is when we calculate s, it's going to be 1.5 times as big as well, because I'm just dividing by the same thing, but something that is 1.5 times as big. So moment from weight will be larger, so s will also be larger.